Thank you, Mark. Thanks, everyone, for coming back. So, so today, well, let's recall that last time we built, in some sense of the word built, a category of motivic spaces over some base B, and as well as pointed spaces over B. And we can go between these two. We can add a disjoint base point, or we can forget the base point. So in particular, well, okay, we have any smooth scheme over B is giving us a motivic space. So today we're going to do something to this category of pointed motivic spaces and get motivic spectra. So I'll denote in this talk that category by SPT sub B, what is this? So this is, in it could be a model category as we talked, or a infinity category. It is stable, which means that that its homotopy category is a triangulated category. So there's a shift functor, and things like homotopy fiber sequences are the same as homotopy co-fiber sequences. Pullbacks are the same as pushouts. So so that's nice. So the homotopy category is triangulated. So that makes it pretty easy to work with, or at least comparatively easier when we try to study spaces. It has a functor. So we have a functor from spaces, or pointed spaces really, then we can compose if we want. That's called suspension infinity, and sometimes people decorate it with a P1. Sometimes people also call these things P1 spectra, but those are the only kind that I'm going to consider, so I'm not going to use that notation. And this functor has an adjoint that's called loops infinity. So in particular, every smooth scheme, we can add a disjoint base point and get a suspension spectrum out of it. Or if it's pointed like GM, we don't have to add a disjoint base point. What else is it? Well, there's also this, we talked about the smash product on pointed spaces, so that gives us a symmetric monoidal product here as well. Okay, so why do we care about spectra? So this is the natural home for cohomology theories, at least the kind of cohomology theories that are A1 invariant. Natural. So like homotopy K theory, Motivic homology, but also algebraic cobordism, etc. It's as we'll see in the second part of this talk, from here one gets the sort of maybe I would say the cleanest approach to a relationship between K-theory and Motivic cohomology via an Atiyah-Hirzebruch spectral sequence. So I believe Chuck's going to talk about that in more detail. So this afternoon is all about that. So we have Atiyah-Hirzebruch spectral sequence here. So we'll see how this comes up later. Other things that happen here are that so finite étale maps of smooth schemes over B end up having transfer maps, so, just like in classical homotopy theory, we have transfer maps going so in the other direction. Let me write it down. So in classical homotopy theory, we'll be talking about covering spaces, and these transfer maps exist on the level of cohomology theories, but here in this category of spectra, they're actually functors in spectra. So the notation for the suspension spectrum of X with a disjoint base point is also that. Okay. And not unrelated to this is the fact that there's also a sort of topological realization for, or sort of, yeah, I don't know. If you want a space level definition or a realization of a Poincare duality, then you need to go to spectra. You need to be in this world. So I probably won't talk more about this, but so if you have projective, to be projective smooth scheme over B, then Poincare duality in cohomology is, or is a statement about the suspension spectrum of X being dual to the Thom spectrum of the stable normal bundle of X. So, so these are analogs of the corresponding statements in classical homotopy theory, and so they get to be realized in this category of spectra. Okay, and so a remark, even though, so I'm not going to talk about the so-called S1 spectra. This category is stable, but it's not simply the stabilization. So it's more than the stabilization, if you know what that means, of, I'll say, of spaces. And the thing that the more that's needed, well, why wouldn't we just do that? So that the stabilization would be just looking at so-called S1 spectra, if you know about that. But to have these things happen, you need to do something more. Okay. Okay. So that's just some hopefully motivation. So to say what this thing is, again, we won't be able to get into very much into technical details, because to do that you need to have a solid technical abstract homotopy in place and chosen, and we didn't do that. That would take too long. So, but in any of the setups you might have, what you're going to do is you're going to look at the motivic spheres. So we mentioned there the constant circle, then there's GM, the Tate circle, and then of course P1, and P1 is going to be equivalent to the smash product of these guys, and maybe more generally, exercise is that, so an minus 0, so that is, so if we take the C points of this, it is a 2n minus 1 sphere, right? Well, in general, this is the sphere, right, okay, so I'm going to write 2n minus 1 comma n, where the definition is that S A comma B is A minus B topological constant sphere and GM B times. So A, yeah, if you take, so this is constant, the constant simplicial sphere. So A is the topological degree if you take or topological dimension if you take the complex points of this thing, and B is telling you how many GMs appear. Okay, so right, so now on to spectra. So I'll do a little bit like Chuck did. He said, well, one notion of spectrum, I guess you call it quick and dirty. I don't know. I would just say it's quick. It's probably, yeah. Is as a classically as a sequence of spaces and certain bonding maps between them. So now in classical Motivic homotopy, so a Motivic, and again, sometimes we call it P1 spectra, is 20 years ago. Yeah, time flies. Yes. Yes.
And do you have, do your duality theorem, include, as a generalized coherent duality?
Yes, I think
that
so.
Is you, in fact, you have a characterization of exceptional, a kind of generalization of, a spectral generalization of exceptional inverse image.
Yes, yes. There's a whole six-functor formalism, and that's used to get.
I wonder whether it is computed in this.
Yeah, I think so. Yeah, it's exactly computed in that sense, in the using the exceptional functors. Yeah. Okay. Right. So classically, and it's probably even more than 20 years ago. I wasn't there, so it's classical. A Motivic P1 spectrum is a sequence of Motivic spaces xn and maps between them, bonding maps P1 xn 2x n plus 1. And then, of course, you go through the same yoga of worrying about what maps mean between spectra in this setting. As homotopy classes of maps already pose an issue. The symmetric monoidal structure poses, well, it creates lots of headaches. So you want to avoid that. And then ways to avoid this classically started by sort of forming more sort of fancier versions of what a spectrum is. And if you know that classically there are versions in Motivic world as well, so symmetric spectra, for example, or so those are geared towards creating symmetric monoidal structure. From a modern infinity categorical perspective, this is obtained. So what happens is you invert the object P1 in pointed Motivic spaces, or smashing with P1. So in a suitable world of presentable symmetric monoidal infinity categories. Okay, at least the equation is easy. What that means, basically what happens is all the problems are packaged into the machine, so you don't see them on the outside. Okay. So the relation between these two is that if you have, a classical spectrum xn corresponds to colimit of these guys along the bonding maps. So you see why this is an inversion. If you want to invert, 5 on the integers, you take the colimit of multiplication by 5. So that's what's happening here. Okay, so right, so related to that remark above there is that since P1 is the smash product of the circle, simplicial circle, and the Tate circle, this means both of these guys are invertible. So both S1 and GM are invertible. And we use both of them when we talk about things like homotopy groups. So, okay, so to get to there, right? So we already said this. We have this functor sigma infinity plus from smooth schemes into spectra. So we call these suspension spectra of schemes, so equivalences in Motivic spectra are detected by mapping out of objects in this image of this functor, but in fact, so by let's write it this way. We can, so now I get to shift in negative degrees and take suspension spectrum of some x, where x is affine So it suffices to look at affine objects or maps out of affine objects in smooth schemes. So now, because of that, right, so what that means, well, let's come to the conclusion after I, let's say, formally define. Because we have these two spheres, we get bigraded homotopy groups. So pi sub AB of I'll still call this X, of some spectrum X. Well, that's the homotopy classes of maps from SAB into X. So these homotopy groups, they don't detect. By the way, this square brackets just means maps in the homotopy category of spectrum. So these homotopy groups, unlike in classical homotopy theory, homotopy groups don't detect equivalences. But in light of this previous remark, we can define homotopy sheaves, and they will detect equivalences. So what are homotopy sheaves? So I'll denote them pi AB underline. So this is the sheaf associated to the pre-sheaf sending a smooth scheme U to maps I really want to say pi AB of X is a sheaf associated to this pre-sheaf. Okay. But these guys do. Okay. So this doesn't tell you really what spectra are, but it tells you certain properties. Okay, any questions about this? Yes? Possibly. Yes, thank you. How about that? Okay, thanks. Yes?
So these square brackets are mapped in spectra?
In spectra, yes,
So
homotopy class.
Stable homotopy groups?
That's right, these are stable homotopy groups, yes. In any of our settings, we could define square brackets to mean homotopy classes of maps, but I'll be just talking about the stable ones. Yeah. Yes? Nisnevich topology on smooth schemes. All right, anything else? Okay, let's look at some examples. So we already saw that, so this example is called KGL. So we already saw that, algebraic K-theory or homotopy algebraic K-theory is representable in Motivic spaces. So we have this Motivic space K that represents homotopy K-theory. which is just K-theory when the base is nice. So we can actually form a spectrum out of this, and let's see how that goes. Well, if we are writing a spectrum as just a sequence of spaces, all of the spaces are going to be the same K. And now we just need to specify one connecting map. That's from P1 smash K to K. And so this one is, well, okay, so here's a lot of things that are going to be swept under the rug. This K, it has a multiplication. So in order for me to specify this map, all I need to do is specify a map from P1 and now we know what this means. I need to give you a stable virtual bundle. So this represents the class, let's see, O of -1 minus O and K0 of P1. And we're supposed to, well, check that by the projective bundle theorem, the induced map by adjunction, we're going to have a map from K to loops, P1 loops K. So that's the space of maps from P1 into K. This is an equivalence. So this is called as Bott periodicity. Okay, so there is a spectrum. Maybe a remark, I didn't mention this yesterday, is that the space K is not all that mysterious. K is, well, there's a Z for the degree, and then we could look at the infinite Grassmannian, just like in ordinary the homotopy theory or algebraic topology. So we take in, this is a colimit over Grassmannians of n planes in n plus m space, and this is over, there are two colimits involved in this. But another model for this thing is as classifying, or a colimit of classifying spaces for the general linear group. So in this world of motivic spaces, classifying spaces of algebraic groups can be defined, and then we can take the colimit of all the BGLNs as n grows. Okay.
Sorry.
Yes.
Here, infinity spectra, etc. Which one is matrix monoidal? I'm confused because you use mass product for both spaces and for spectra.
Both are symmetric monoidal. What?
You mean delooping and looping?
So in spaces, sigma and So by P1 or, and which way am I? So whichever way they go, I get both spaces to spaces. So there are several things here. One is that there is a motivic space that that is the mapping space. So this is in fact a closed monoidal category, infinity category. So there are internal mapping objects, and loops is this internal mapping object. And this is just an adjunction in spaces, and it becomes an equivalence after stabilization. That makes sense? Oh, sorry. I misunderstood the question.
When it's not.
It is. Why? That's right. Loops is not.
Because here it seems to me you have abuse of notation P1 because P1 identified with S1 smash, and your conclusion is that invertible is in spectrum, so somehow you need some kind of result.
No. Suspension with respect to P1 is composition of first suspending with respect to Pm and then with respect to S1. So if you have,
right.
If the suspension is invertible with respect to P1, then there are two factors in invertible. That's all.
All right. We can talk about it more later. Okay. Any other questions about this?
Can you comment about what's hidden in these statements? Because one thing is that certain thing is representable in spaces, right? So that
Yes.
one is representable. So what else is hidden? So what are the facts?
I think this bot periodicity. That's.
Why is it relevant here? What's the
I guess it's not really, well, it's relevant for the having the representability afterwards as well, because we already got that it's representable on the space level, and then if you want that stably it's the same thing, you need that's an infinite loop space of some sort, or something along this line. Yeah. Okay. All right. So, okay. Other examples. So, an example that I won't spell out, but so just like in ordinary homotopy theory, so well, okay. So tomorrow I will talk a little bit about the connection between motivic and ordinary homotopy theory. And I've already started talking about such things by saying take the C points if we're over the complex numbers. So if we're over the complex numbers and take the C points of this KGL, we get complex K theory. There's also an analog of real K theory in this motivic world. But that's much harder to write down, so I won't. Okay, so continuing on with the examples, skipping that. We'll say KO, or some people write it KQ. This represents Hermitian K theory. But I won't say anything more about that. Now, an example that Chuck talked about is motivic cohomology. So motivic cohomology lives in this world. So I'm denoting it by just HZ. Sometimes in the literature it's written as MZ. So this is more in line with the ordinary homotopy theory notation. So now we're restricting to K perfect field. I'm not sure what the state of affairs is in higher generality. So there is, so we need to write down a spectrum. So here we can write Xn to be this discrete pre-sheaf that Chuck talked about, Z-ter, he was taking GM. I'm going to take P1 to the nth, just so as not to mess up my indexing around. But this is, of course, this is just an n-fold shift by this S1, giving you the sort of triangulated structure of the thing where you stick GM here. So this is a pre-sheaf, and I'm using the pointed version, so it's a pointed motivic space. And we have connecting maps. So what are they? So there's maps from okay, there's a map from here to just from P1 to this pre-sheaf Z-ter P1, and then there's a multiplicative structure to be used as well. So this one is coming from a multiplicative map in unpointed world. It looks like that. Okay. So the theorem is that this represents motivic cohomology. Okay, and then, right, so what more to say? I don't know, a remark, again, in comparison with classical homotopy theory, this is not Eilenberg-MacLane in the sense that it just has one homotopy group, right? So, for Z, it's a little bit harder. Well, why don't we first define? Well, we can do the same way to define, say, H Z mod L, right? Chuck already did this, and so it's easier to say here. So this is also a theorem due to Vygotsky, is that if P is different from the characteristic of our field, and K contains a primitive Pth root of unity, then there's an isomorphism, so we can compute the homotopy groups. Oh, I changed, yes. Let's do this so I don't mess it up again. Okay. So P. So this is up to reindexing or taking negatives of the stars that I won't worry about. So the homotopy groups of the spectrum are the motivic cohomology of K with coefficients in Fp. So this is isomorphic to the Milnor K theory of K mod P, and then an extra generator tau. And you may or may not know what these things are, so it's pretty easy to say. So this K star is generated, is a graded ring. So it's generated by degree 1, where so K1 Milnor is isomorphic to the units in K, and so an A here is written as a square bracket A here, because we have multiplicative notation there and additive here, and then their relations. So subject to the Steinberg relation, A1 minus A is 0 for A different than 0 and 1. Okay. And then tau is defined using the pth root of unity. So this is, I won't say, maybe tomorrow if I have a chance I'll say more about what tau is, but well, I don't know, it doesn't take that long. Let's do it. So tau is, well, it's in H01, okay, with FP coefficients. Well, that thing, I guess Chuck told us about this yesterday, I think, is the kernel of H11 algebra P with Z coefficients, and that's K, the units in K, right, to itself. So this is take the pth power, and so in that kernel we have a primitive root of unity by what we said. Okay. Okay. So the point of this was to emphasize in a very specific way that the homotopy groups of this Motivic homology are not that simple. There are probably many, many other points to be made about this, but I won't do that. Okay, so other examples are that MGL can also be made very specific. If you know about classical cobordism, this is constructed the very same way as a P1 spectrum. Okay. And then, of course, I guess I already mentioned this, we have suspension spectra, and one particular one is the sphere spectrum. That's right. And so that's the suspension of, I guess, B in the general. B is the terminal object, so this is a point. And I'll write that as S00, because we have now bi-graded spheres. Okay. Are there any questions about any of these spectra? Okay. So the next thing to talk about is, well, how to, I don't know, well, how to study the spectrum. What can we do with them? How do we approach them? So in classical homotopy theory, there is the Postnikov filtration tells us how to sort of decompose a space or a spectrum into Eilenberg-MacLane objects which have easy homotopy groups. Now here, this is the goal of the slice filtration is again to decompose an object into this sort of Eilenberg-MacLane type objects, except not quite. So we want things like Motivic homology or well, something else. It turned out modules over it, which, again, the sort of analogy breaks because things get more complicated, but maybe Chuck will tell us more about what sorts of things appear as slices. So that's the goal, is to decompose things, but not by the vanishing of homotopy groups, but rather by things that are governed by the Motivic cohomology spectrum. So to be more specific, so for an integer n, we define spectra greater or equal to n. So it's a full subcategory called n effective spectra. So this is the full and stable subcategory generated under colimits and extensions by what? By things that are suspension spectra shifted by P1. I haven't introduced it today, so P1. Smash that. For X being a smooth scheme. Okay, so another thing that doesn't compare well in this analogy with the Postnikov tower is that this is a stable subcategory. Now that we have sort of two kinds of spheres to play with. So basically, this is telling us how many GMs can there be, can we desuspend by in our spectrum, but we can suspend or desuspend by as many circles, simplicial circles, as we'd like. Stable means that its homotopy category is triangulated, or it's probably not the definition, but so S1 is invertible in this category. That's right. I allow either shift positive and negatives by S1, but not negative shifts by GM. Positive shifts by GM are allowed because it's a scheme. Okay, so this gives a filtration that's called the slice filtration. So we etc. And so I've dropped the subscript just to save chalk and time in writing. So these inclusions, the n-effective spectra into all spectra have a right adjoint, Rn. Adjunction. And so this is an adjunction such that if we look at this composite, so that's the composite where if we first do In and then Rn, that's homotopic to the identity, but so it's a kind of localization, and we define Fn to be the other composite. So we have a natural transformation from Fn to the identity. And this is by sort of construction for any spectrum E, Fn E to E is a universal map from an n effective spectrum to E. So, so we also get natural transformations between the Fn's by sort of formal properties that follow this. Entity. And the slices are called the cofibers of these maps. So this is Sn. So that's defined to be. So, okay. So every time you have a filtration, it gives you a spectral sequence. And if you are a homotopy theory inclined person, you want to compute all that you can about it. You do not assume that it collapses or hope that it collapses. You hope it does not. All right. So in any case, so you get the slice spectral sequence. And so what does it look like, up to worrying about where the indexing is. So this is a tri-graded to bi-graded spectral sequence. So it's going to start with the homotopy groups, bi-graded homotopy groups of the slices of E, and it's going to try to compute the homotopy groups of E, but not quite. So there's convergence issues. It really converges to something that's called the it doesn't always converge to those homotopy groups. So it converges to what's called the slice completion of E. Or rather, it's the homotopy groups of the slice completion. And what is that? Do I have time to say that? I don't know. Well, formally what it is you take for each of these maps from Fn here, and we call those F upper n of E, and now you also have maps between these guys, and you take the homotopy limit of there. We only have convergence here if this is an exhaustive filtration, right? So you would need that the inverse limit here is contractible, which would mean that the inverse limit of these guys is equivalent to E. So, so that's what it is abstractly, but then it's a theorem, and now I forget who proved this theorem. That's okay. That this can be identified. All right. So, okay.
And can I clarify
Yes.
whether this is a T-structure?
No, this is not a T-structure.
But T-structure with trivial heart. So think of it that way.
Oh, really? Okay.
But it's,
Yes.
in any
So there's a related related notion called the very effective slice filtration, where both sort of GM and S1 suspensions are bound, and then there's also I guess what's called the homotopy T structure, and there are a ton of relations between these three notions you might want to read about or work out by yourself. But anyway, so I promised to say something about this Atiyah-Herzberg spectral sequence, so maybe I'll move on to that unless there are other questions about the generalities here. Yes?
When we took the cofibers, get the slices, is that like already that object values? Because like this with the
You're taking the homotopy fiber in the category of spectra. If you might need to worry about, I never remember these things off the top of my head. So whatever's the correct notion, it may be object-wise, but you might need to sort of do some kind of localization to the object-wise construction to get the cofibers.
S1 spectra do it object-wise.
I see.
What's the object of not a spectrum?
That's right. Yeah. Okay. All right. So, right, the whole point of this is that, well, the slice spectral sequence in an example is going to give you the Atiyah-Herzberg spectral sequence. So, the two relevant properties are that for the Eilenberg, or well, for the Motivic cohomology spectrum, F0 of Hz is already Hz, so Hz is effective, is zero effective, and but also S0 is that. So F1 is trivial. So this Hz is its own zero slice, and it doesn't have any other slices. And the second one is so I guess for both of this, I am working over a perfect field. Is that S naught, well, okay, one thing is, okay, S naught of AGL is Hz, of KGL is Hz, but in fact, by this periodicity, we get that then all slices are Hz, suitably shifted. So this is going to be 1 and smash Hz, or you can write it in a multiplicative way as this whole thing. So in classical homotopy theory, the homotopy groups of this KGL are Laurent polynomials on the Bott class, and here that's captured in the slice filtration where this beta, let's say, is the class of like S1, for example, or -1, depending on your conventions. And so the slice spectral sequence in this setting, let me just write that out here. It's if I have my indexing right, it's going to be Motivic. So here I'm not just taking. Oh yes, thank you. I see. And now, oh, I see. I just wanted to pick out the algebraic K-theory part. So I'm just, there's more stuff here. Yeah. Okay, minus Q. Okay, thank you. Okay. So we get, so the slice spectral sequence is a trigraded piece, and then in it there's this bigraded piece that picks out the Atiyah-Hertzberg spectral sequence. Okay. So, yeah, maybe I should stop here. Thank you.
Any questions? I do have one question about the definition of on the cardboard in the middle. Well, you said the filtration comes as a GM as a scheme, right?
Yeah.
I guess what concerns me there is wouldn't you want like GM's already pointed?
Yes.
You want like to suspend infinity with GM once it's solved with this.
Oh.
So it is like a suspend infinity of pointed scheme. It's the code as opposed to the code.
Yeah, it's not going to matter. You can take that point out. Wait a- Yeah. You can get rid of the point. Yeah.
Other questions?
Could you please add some details about that factor because it's bigraded because I don't know which framework will lead to this kind of vector sequence. In future spectra is just
Well, we're applying we have a single filtration, so, but we're applying a bigraded functor to it by applying homotopy groups. Now we have two gradings in the homotopy groups.
so what kind of, for example, connecting motives, etc. I mean,
Differentials?
yeah.
You're going to apply homotopy groups to these guys, and then you're going to have the same kind of thing if, I don't know, if you start from the E1 term, you have these things, and you chase through everything and you figure it out. I'm not sure. Yeah.
One quick
Yeah.
comment. You have 3 stars there. Pi star,
Yeah.
star, S star. The
That's
second
right.
star is fixed.
No.
It's the same as the second star.
It can be, but it doesn't have to be.
But I'm saying in the differentials, it doesn't change.
Oh, I see.
That's
Okay.
what I mean.
Oh, right. Because all we're doing is we're moving by these suspensions, desuspensions. So the differentials are not going to change the second star in pi star star. Thank you. Yeah.
Oh, any other questions? Okay, then let's meet again in quarter 2, I guess.